Specifically, the topic today is on when good programs go bad. Okay? We've been talking some about the use of testing and developing confidence about a program. We've been talking about good style and helping prevent gratuitous errors for good naming by encapsulating things and functions so that we can go to one place for certain types of functionality. We have a separation of concerns. We have clear bases for testing and for modularity where we can replace pieces. And these are all extremely important. But ladies and gentlemen, we live in an ugly world. And the best of written programs can have bad things happen to it. These bad things are of different sorts. And we're going to be discussing 3 different types of sorts of bad things today that can happen to your program and 3 different ways of handling them. Return values, exceptions, and assertions. And I want you to be clear about the distinction between these sort of different classes of things so you can be guided as to the right mechanisms to use. So you don't use a return value where an assertion is required. So you don't throw an exception where really a return value should be used. Okay, so what sort of bad things can happen to a program? Anyone? Okay, you can have a null pointer exception. What might be so that's a failure, that's a surprising thing that might happen. What might cause a null pointer exception? Memory exhaustion would be one thing, for example. Or maybe a file can't be located and it returns a null pointer indicating there's no such file. You don't initialize pointers properly. So some of these things are going to be bugs in implementation, but we're going to be concentrating today predominantly on things that even a very, very good program can go wrong with it. Even if it lays out the contracts that we talked about last time, lays out what's assumed, what needs to be passed to it, even if it's correctly implemented, bad things can go wrong. What other bad things can go wrong in programs? So we've heard some, and absolutely. Like memory is exhausted. You don't have control over that. You could have a great program, but memory is exhausted. You could have a great program, but disk is corrupt, right? What other things can happen?
Communication error.
Communication error. You're assuming a network connection, and that network connection is not available. You're out on the farm and the cell service is spotty and you can't get access to maps or what have you. These things are realities of the situation. So resources are not available, for example. You don't have access to disk or network or memory, databases, which are going to be at the core of a lot of larger systems that you're going to be learning about later in your computer education. Sometimes the database may not be available. It's being WAM'd by some other application. Maybe it's been brought offline. Maybe it's experienced an error. Maybe you're being starved for CPU cycles. You're assuming that you're going to be able to get work done in a reasonably efficient way, and you're not able because something else is chewing up lots and lots of the CPU time. In other words, it's getting lots of work done, or thinks it's getting lots of work done. There are also cases where we have end-user errors that lead to unexpected things happening. The user specifies a file to open that doesn't exist, or it's the wrong type of file. How many people ever have done that? Specify the wrong type of file for a program? I know I have, certainly. Yeah. I mean, it's almost universal. And the program goes and looks in there and says, "What in the world is this?" You might use other language, and it has to react to it, right? Or a situation where you think you point it to a legitimate file, to a legitimate type, but that file is truncated. It got chopped off at least. Some data was lost from it. It's only got half a file there, maybe because your disk was full and you copied it there, or something like that. It's a bad thing that can happen. Data corruption can happen. A disk can get messed up. These days, file systems are designed to be more robust in case there is corruption. But we can still have a situation where the file that we're counting on has scrambled contents. Maybe the program that created it was sloppy, or another program that was using it was sloppy. It didn't clean up after itself, and it crashed in the middle of it and wrote some half-digested contents. Another thing that can happen is if we're providing libraries, for example, we may say, hey, we're going to assume with our contract that you have to pass me something that has that's a legitimate pointer. It's not a null pointer. But the person who actually calls me ignores it. They overlook it. They try it anyway, hopefully. They don't understand what the specification means, and they end up passing you something that you said you're not going to handle, or that's not allowed. Often what happens is not merely those sort of oversights, there's reasoning failures. So we forget about the fact that this pointer that we got could be null. We pass it to another function which counts on having a non-null pointer. We have a failure of reasoning. We forget about that awkward case. Okay? Do these things happen? Big time, folks. And when I'm teaching the upper level courses, something like 371 or 470, I see these things all the time from your upper level students. So, people forget about the awkward case. All too often as programmers, what we do is we focus on the typical case. We have some idea of what value our program's adding, what work it needs to get done to add value to people's lives, what job it accomplishes, and we focus on that at the cost of kind of thinking about those awkward situations where it can't get the work done because of X or Y or Z or what have you. And ladies and gentlemen, within your professional lives, within your careers in the software area, you're going to be dealing increasingly with systems that are dependent on lots of other resources. Time was, programs ran in a self-contained way on the machine, and if you want to transfer data to another machine, you use sneakernet. You plugged in a floppy drive and you got out something, you walked over to another machine. In the late 60s, 70s, and into the 80s, you saw real network computing, but it really took off in the 1980s and 1990s in the corporate world and broad use outside of academia and outside of research. And these days, typically, a program that you write will need lots of resources. It will need to go over the web to snarf some data off of some website. It will need to connect to a database which is located potentially somewhere else. It will need to send data back to a server or something like that to send off an email message or what have you. And all of these are points of failure, points of possible failure. So no one would be at the luxury of just kind of having total control over our surrounding environment or understanding that surrounding environment in great detail. There may be lots of things occurring elsewhere. So these resource failures in your professional lifetime are going to be one of the key things that you have to deal with. And it is an absolute recipe for disaster, and one that's written about, if you depend on, for example, network resources as if they were insured. Because they're not. Because it's a total fiction. It's just ludicrous. It's like driving as if there's no stoplights. And ladies and gentlemen, in both cases, you're likely to encounter a crash. Okay? So we have to deal with the situation about when bad things happen. And we're going to be talking in this lecture about handling the bad things that happen of three different sorts. They say that when you give a talk, you should tell them what you tell them, then you actually tell them, then you tell them what you just told them. Okay, and so I'm telling you what I'm going to be telling you. So here, we have three different ways of handling types of bad things. For certain common events that are sort of expected, that are frequent, we can anticipate we're gonna get one of these events. An example would be an end of file. We're going through a file, and we know that the file's going to end eventually. We know there's going to be an end of file, and we have to be able to handle it. We can signal those sort of things with return. These are sort of special values that have a certain meaning that indicate for us that we've gotten something unusual. So, for example, you folks have written while loops where you have, get char, and you say while it's not equal to EOF or something like that. So this is a sort of a special value that we use to encode. And I call it here return code because that's one use of it. And Unix, Linux, and C, and many other programming languages have just return codes up the wazoo. So you have a return call for error and a return code for OK or something like that. In fact, Unix commands, like when you do a cat or when you do a sword or what have you, they actually return codes. Okay? And there'll be things like 0 or -1 to encode things. So there's certain types of things that can encode by just passing back a special value that we all agree has a specific meaning associated with it. Okay? So that's one sort of. A second common expected event we handle with return codes. Unexpected events that are going to occur. We can't avoid the fact that they are in fact potential events which could legitimately occur in the context of running a program. And we gotta clean up after them. Those sort of events that are awkward, that are inconvenient, that are not to be expected, not like an end of file, which you know is coming, but which can definitely occur, and we have to handle with exceptions, okay, most likely. Now, C has a kind of particularly primal, sort of crude form of exception handling. And so C is, if you could forgive the pun here, C is kind of the exception here. It's a language that originated before a lot of the theory associated with exceptions was formalized. But you folks have already seen exceptions in 270, right? Is that right? Yeah. Okay. I appreciate the Greek chorus. That's great. Thank you. Excellent. So exceptions are used to handle these. What may not have been given to you in 270, but typically not, is sort of done on when you use an exception. Should I signal an EOF with an exception? Should I signal, a file unfound with an exception, or should I signal that with a return? We're going to be talking about those sort of things. The final type of thing we're going to be talking about is the issue of assertion. Now, these handle a different class of bad situations. Logic errors, developer mistakes, things which should never occur, ladies and gentlemen. But the truth of the matter is, they do occur because of human oversight, because of human reasoning failures and so on. And we want code that tells us, we want code in place that's going to tell us as soon as possible if things like that are going on. We don't want to just blithely ignore them, pretend as if they're not happening. We want to be engaged in what's called offensive programming. If there's errors out there, we want to go out and find them as soon as possible so that they don't end up corrupting data throughout your program. Don't end up leading the user to get a result that may seem useful but is totally off base, totally wrong. Okay? So assertions, ladies and gentlemen, are very different than the two upper types of situations. Here, with assertions, this is something we should never see if the program was putting together good code, had very solid reasoning. It may be things that we've said, hey, don't call us with a null pointer, for example. Don't call us with an empty array, but someone does. It's like you walking into FedEx, they say, you know, you gotta get the package here by this time to have it delivered by 5 p.m. the next day, and you don't come in by that time. Or it's like, you know, this is not to put ideas in your head, but you know, for drop date, you have to drop a course before a certain time, and you come in after that time. And say, I'll drop. They have to be able to handle that somehow, right? It's not something we expect to happen. It's not even something that's sort of, it's not something that's legitimate, but just sort of unexpected. It's something that we've said shouldn't happen, but it does, and we have to be able to handle it. So we'll talk about those sort of classes and the use of assertions. And we'll see some examples of those as well, quite a few. Okay, so these are 3 classes of bad things that can happen. Sort of common expected events that definitely we need to be able to handle because they're going to happen fairly frequently. Unexpected rare events that we definitely have to handle because they're going to happen on a rare basis. They're perfectly legitimate things that can go wrong, like a distance fold or whatever. We have no control over that. And finally, things that are results of logical errors, and we want to be able to know about those logical errors so we can root them out of our program as soon as possible, or alert the person who's put them in so that they can fix them. Okay? So I'm going to here stop.